Okay, let me get back the slide, first of all. First of all, if you look at the web page of the course, and let me do like this, just 1 second. Give me 1 minute. I want to get a visualization that is more convenient. If you look at the list of lectures, there is one more today, assessing water resources availability in inductive methods, and also there is a link in this previous lectures. I put a link to the PowerPoint presentation that I am using. If you look here, at the bottom of the page, download the PowerPoint presentation. I don't think it is really useful for you, but in any case I wanted to make it available. And may be useful for you if you want to follow on your PC what I'm projecting, but I don't think it is really needed. And then let me get it. Okay, here it is. I think it's better if I connect the power. Okay, now we were here. Increasing water supply. This is, as I said, we talked about, the previous slide was about water resources availability. And in some countries, as we will see also later, there is a situation of water scarcity. Water scarcity is defined as lack of freshwater resources with respect to water demands. This is the definition of water scarcity. What I suggest you, in my web pages, there is a link on the Wikipedia page of water scarcity. Have a look at it because it's interesting. It's just descriptive, but I suggest you to have a look at some statistics that are there. You don't need to read everything, just the introduction is fine, and if you're interested you can move forward, but it's not needed. So water scarcity is sometimes, it's in practice a lack of water. And I tell you once again, when we talk about water scarcity, it means that this is permanent. It may be only for some months in the year, typically is. It is only during the drought season, but it is repeated almost every year, if not every year. So this is a necessary condition to call it water scarcity. It means that it's permanent in the interannual direction. It's not necessarily permanent in the intra-annual direction. So it's not necessarily permanent along the year, but it's permanent every year during the dry season. It's different from drought. Drought is the occasional situation of lack of water. So when we talk about drought, it means that normally we don't suffer from lack of water. But there is an event in which we suffer from lack of water. The consequences of a drought sometimes are very, very significant because, you know, you may get used to a situation of water scarcity. You may find solutions for resolving a situation of water scarcity. The unexpected occurrence of an event, of an extreme event, drought is an extreme event, of course creates a different type of problem. And we may not be prepared to face it. So you don't have to think that drought is less significant. It's less impacting because it's occasional. Sometimes the occasional event is more and more impacting. Whatever is the measure that you use to quantify the impact. It can be loss of lives, it can be economic impact, whatever is the measure, sometimes an occasional event, which never happens, it happens once, think about a flood, it's more impacting with respect to a regular situation of crisis. So, if we experience a water scarcity situation, typically humans try to secure more water. And this is what humans always did. So the Romans built the aqueducts, and in the modern times we build reservoirs. We build dams. We use natural reservoirs like lakes in order to increase our access to water. What we realized recently is that securing more water has a strong environmental impact. You don't have to think that this water is lost, absolutely not. If we bring more water to a city, at the end of the story we give back the water to the river. Maybe it's polluted, but if we treat it, not necessarily it's polluted. But along the way, from where we catch the water to the city, of course we deprivated the land of some water, because we put the water into pipes, etc. So we realized that this solution is impacting, and we realized it only recently, because think of the situation, for instance, in Europe, where up to 1970 we didn't have any rule for imposing the release of an environmental flow. The environmental flow is something that now is imposed by law. What does it mean? It means that when you project, you design a withdrawal of water from a river or from groundwater, you are required by law not to use all the water there, but to make your withdrawal sustainable, which means if you get the water from a river, not to get all the flow, but to release downstream your withdrawal, to release downstream a part of the flow. This is called environmental flow, and we have rules for determining it. Up to 1970, there was no awareness that getting all the water from a river was causing a strong environmental impact. And you may think, how is this possible? It's possible because, of course, it's very logical. If you project, design to take water from a river, it's very convenient and logic to take all the water. And we realized only later on that there were impacts downstream in terms of water table that lowers down, in terms of several consequences and ecosystems dying, but the value of ecosystems was recognized only recently. So basically, this is a new concept, the fact that increasing water supply has significant environmental impact. So starting from very recently, up to, I would say, 20, 30 years ago, we start thinking at alternative solutions. Okay, but keep in mind one thing. I already mentioned to you the importance of social learning, which includes learning how society develops and how society reacts. Now, if you build a dam, a huge reservoir, people are very reassured. They feel relaxed because they see a lot of water. So this is a solution that, in general, it's very popular among people who suffer from water scarcity because they can clearly see the solution. Of course, it is unpopular among people that are concerned about the environment. If they don't suffer by water scarcity, because they may be located upstream where you build the dam, they are not interested in building the dam, so they get concerned for the consequences. And this is something that we have to learn, something that we have to take into account. Because today, everything you do cannot be imposed anymore, or it is our current culture. It's very difficult to impose a solution. think about the public debates, about the public contestations that sometimes we get when we try to build a new railway or to build a new dam. It's almost impossible today to build a new dam because there is opposition of society. So this is something that we have to learn. When we propose a solution now, the engineer is required also to think of the social consequences, because in some cases the solution may be technically feasible but not doable, not for economic restrictions but for opposition of the public. Okay, so what are, first of all, let's have a look at this interesting picture, the cost of water supply. It is extremely important to take it into account. This is an economic component. And it's interesting to look at this picture. Sometimes you see the range that is wider because it depends on the type of supply that you secure. And also keep in mind that this is referred to the US, so you see reference to US average, Southern California. In Europe the costs may be different. So groundwater in Southern California, it costs about how much? Keep in mind the units. So what is in the axis? It's conventional water treatment costs, and here cost for cubic meter of potable water in US dollars. So you can assume that $1 US is €1 or less, but cost per cubic meters. So in this case we have from 0.3 to 0.6 dollars per cubic meters. I give you this information. The potable water here in Bologna costs about €1 per cubic meter to the customer. To me, it costs about €1. How much is a cubic meter? This is extremely important for you. You have to be dead sure that a cubic meter is 1,000 liters. Okay, dead sure about that. It doesn't have to happen that I ask you at the exam what is how many liters in a cubic meter, and you say 100. Okay, it doesn't have to happen, because this is one of the things that you cannot make wrong in an interview. So I am rigid in the same way. Okay, keep in mind 1 cubic meter is 1,000 liters, and you may think, okay, but this is really a lot, so it's not a huge cost. But keep in mind that when you take a shower, you consume from 20 to 50 liters of water. You don't realize it, but this is actually what happens. Okay, brackish water. What is brackish water? It's water that has a salt content higher than that of fresh water and lower than that of seawater. It's in between. So it's water that you can easily use because, for irrigation there are some crops that can tolerate some salt, or anyway, in California it's convenient to use it. And where do we find the brackish water? For instance, in estuaries. In estuaries you have a mix of seawater and river water, and it is very convenient to use it because you have a lot of water in the estuaries, more than upstream because you have some seawater coming in. So it's very convenient to use it. In some situations you can use it. Even to distribute the water to people for city use, if salinity is quite low, you can use it. And you can also separate the distribution system. So use this saline water for other uses other than drinking in the homes, like for the flushes in the toilets or something like that. And that's fine. Okay, conventional water treatment in user average. So conventional meaning mix of surface water, etc. User average. I think this conventional includes also the groundwater. So this is the average in the US for average cost for producing drinkable water. Surface water in Southern California, usually keep into account that surface water is cheaper than groundwater. In this case, probably they have a condition that makes surface water available at the same price as groundwater. In this region, for instance, it's not the case. Groundwater is more expensive because it depends on the depth of the water table. If it is very deep, you have to pump a lot of energy for pumping. If it is close to the surface, it's more or less, it's the same thing as surface water. It depends on the local conditions. Treated wastewater, you see that it's quite costly. Usually the cost is higher. Maybe that in this case they have ways to optimize the treatment. And then desalination. This is one thing that I wanted to show you. Okay, in this case the range is thinner because probably in Phoenix they have a fixed cost. If you go to the global average, of course, the cost of desalination depends on the location. But you see that more or less Phoenix is located in the middle. Desalination, this is the message for you, is still not sustainable. It is very costly. So unless you have a lot of energy available at a low cost, because you need electrical power to desalinate, unless you have the way, a means to get cheap energy, it costs a lot. And usually, where do you have the way to find a cheap energy? In the mountains where you don't have the sea. So this is another reason why desalination is in the mountains you have cheaper energy because of hydropower. And this is another reason why desalination is expensive. So you see that there are costs associated to it. And so, alternative solutions, water demand control and regulation, this is one possibility. It means that, let's talk about water losses first of all, reducing water losses. And unfortunately, if we look at the situation in Italy, which is representative of the situation in Europe and in the US, it's not much worse. If we look at water infrastructure, water supply systems for irrigation, these lose about 50% of water by infiltration and by the water losses due to management, like when you have to empty a canal to clean it, of course you may be forced to empty it when by just releasing the water in a not useful way. For instance, because you are required to clean the canal when farmers are not asking for water, for instance during a rain season, and this is lost water because there are no water demands. And also you may need to empty the canal for technical reasons, because some technical problems occur, and of course you have to release the water where you have the technical problem. So not always you can use this water in an efficient way to cover some demands. So water losses are about 50%, which is an enormous rate of loss. Unfortunately, more or less the same loss rate is experienced in water supply systems for civil use in aqueducts due to water losses of the pipes. And keep in mind this is a huge problem and it's not easy to solve. Sometimes you see people saying, what's the matter here? If a pipe is leaking, let's fix the problem. But it's not so easy. First of all, because you have to find where the leakage is. And there are techniques that were recently developed by using modern instruments for monitoring, but it's not easy, first of all. Second, you need economic resources for substituting a pipe. So it needs money. Keep in mind that this is an interesting thing that I wanted to report, some distinguish about real water losses, and I was talking about real water losses now, and apparent water losses. What are apparent water losses? It's, for instance, unauthorized use. There are some people who use the water and they are not authorized, so they don't pay for it. It's very easy in some cases to use it. For instance, in your home, if you find a way to bypass the water meter, you are using the water without paying it. And if you think of it, it is very easy to bypass it. And people usually don't do it because it's not a big expense. But we can imagine that some people that use a lot of water may devise a simple bypass. And this is an apparent, it's called apparent water loss. So we see it as a water loss because we don't get the money. We distribute like 1 cubic meter of water, and we get money for half a cubic meter. So we think that it's a real water loss, instead it's an apparent water loss, which is in some way less concerning because it's not a real loss. On the other hand, of course, it's concerning because we need the economic resources in order to ensure sustainability. And therefore, at the end of the story, the effect is not much different, the impact. But reducing losses is a possible solution for solving water scarcity problems. Usually people don't like it because they don't see it with their eyes. Another instrument is pricing, which is demand regulation, which is another story with respect to reducing losses. It's a third solution. A third solution is regulate the demand. And how to regulate the demand? There are several ways. And for instance, you can use taps that save water in the homes. And for instance, in Italy, we have several water boards who distribute for free special taps. And the purpose is to reduce the flow when you open your home tap. This is a way to regulate demand. The most used way to regulate the demand is pricing. Of course, if you increase the price of water, you have a reduction of water consumption. And usually, you know, it's a reduction, it's a beneficial, it's a good reduction. And this is a solution that is widely used. Another solution is try to reduce the impact of extremes, which means if your concern is drought rather than water scarcity, we can make the system more resilient, which means the system is, we defined resilience last week, which means that the system can absorb shocks more efficiently. This is another way. I leave to you reading this because it's very descriptive. And let me conclude this lecture in this way. We made a brief survey of possible solutions. The problem is that when we turn to the design, we have to identify the best one. And after this introduction of this course, I'm now moving to the design part. So, in general, what is the design principle that we can follow? We have a problem to face. It's a problem of water scarcity. Keep in mind that if you don't have a water scarcity problem, you don't have any need for water resources management or thinking about sustainability unless you see in the future a water scarcity problem. But in any way, you have to see either presently or in the future a water scarcity problem. In this case, you need to get involved in sustainable design and water resources management. If you have enough water, there are places in the world where they have enough water, sustainable water resources management is not a problem for them. If you go in the north of Europe, for many reasons, they have plenty of water. For climatic reasons and also for the reason that their agriculture is not as developed as in Italy, where the climate is more favorable to agriculture because temperature is higher, but usually where you have higher temperature, you also have less water for evaporation, etc. So in the north of Europe, they are not very sensitive to water scarcity, water resources management. In Italy we are, of course. In Spain they are, more than in Italy. In Greece they are. So the problem is, how should we how should we solve this problem? And there is a traditional approach. The traditional approach, which was widely used recently in view of the increasing concern caused by climate change. The traditional approach is to make a projection of the future situation. in terms of demographic expansion, in terms of future climate, in terms of future water demands. So one makes a projection. When you do that, usually you adopt some allowance for freeboard, which means a safety coefficient. So if you are uncertain about future climate, what you do is, let's assume that the prediction is 20% wrong, meaning that I need 20% more water than predicted, because this is a safety factor. Okay, this is a usual approach. As engineer, we adopt safety factors. And then you get an estimate of the future situation. And then you design what's needed. So, okay, there is a water scarcity of a certain amount, I need a dam, because I cannot resolve the problem by reducing the losses. Then you estimate the costs, and then you start the interaction with people and administrations to find the optimal solution. And usually, you have a big problem here. Apart from the opposition of the public, because they still don't see the problem. They may trust your projection, but still they don't see the problem. This is one problem. The second problem is that because you adopted safety coefficients, your estimate of cost, your cost estimate is quite demanding. Building a dam, it requires a lot of money. And therefore, you get the problem that your solution is not sustainable. This happens very frequently in Europe. If you think about debates about water resources, recent debates in Italy, this was the workflow, like projection, estimate of the costs, opposition of the public, and unsustainable solutions because there are no resources. This is a situation that needs to be resolved in some way because we need to act. And therefore, it was proposed recently to revert this approach by considering the so-called bottom-up. So the approach that I just described is termed top-down. Starts from projections and then down to the solution. The bottom-up approach reverts, as I said, the workflow. So where do we start? We start from the population and their problems. We currently have water problems, water scarcity, whatever, and we focus on the problems reported by the population. In this way, we give a kind of reassurance to people that we are starting from their needs. And then we identify the solution that maximizes the resilience towards future developments. But the solution must be doable. So, if we find, let me make an example, if we find that some people need more water for irrigation, then we find that there is the possibility to compensate their request by reducing losses. Okay, this is a possibility. So we solve the current problem by reducing losses. Now, let's ask ourselves, but what is the best solution to ensure the durability in order to make sure that even if climate changes in the future, still water scarcity is not experienced. And we may find that water losses is fine for the current situation, but cannot compensate if there is a reduction of water resources up to greater than 20%. And then we can prove to people that if they build a dam, there is compensation of the current problems, and also under the assumption that climate change causes a reduction of 50% of the water resources, still they will not suffer. It's a different approach. And then we may conclude, like in many cases we do actually in practice, okay, reducing losses is not really costly, it solves the current problem, so let's start from this. And then, if in the future the climate changes, if we have a reduction of water resources, we can still build the dam. If we build the dam now, this is not possible because we don't have enough economic resources, and also keep into account the duration, the lifetime of the dam. It's 100 years. And therefore, in 2100, when climate change will occur, the dam will not work anymore. So it's a different approach. On the one hand, we start from projections. On the other hand, we start from local problems. Keep in mind that this is a proposal, and this was proposed about 10 years ago. And people don't like it very much, not yet, because still they think that by looking at how to say, hard solution, structural solution, by looking at a dam, they feel more relaxed. But this is probably the future. And it is probably the future because we are realizing now that climate projections are not as reliable. And this is a recent discovery, because if you go back to 10 years, there were climate projections predicting for these years, these days, a much worse situation than what we are currently experiencing. And now, you know, we have climate projections saying that in 10 years we will not have enough water for agricultural production, but people wonder whether this is true, because of course they look at the past experience. So the debate on climate projection is really a bit hard to follow, and therefore this is the reason why some researchers propose to start from current situation and make the solution resilient against climate projection instead of designing solution in the face of climate projections. This is something that it's really tricky, but anyway. Okay, and this is the sketch that I should have shown you before, but in any case you can find it on my website. Okay, now let me move forward to the next lecture, which is, just give me 1 second because I need to update my personal computer by synchronizing with my PC in Office. Okay, let me do this. Okay, lecture 2. This is not yet linked, but I will link it soon. And the next lecture is, of course, there is a web page for it. It's assessing water resources availability, and we are going into the more engineered part now on technical subject. This is very classical. Of course, I will make reference to sustainability while we learn how to assess water resources availability. This is the basic question that we have to resolve before we start designing. How much water can we use? And also, we can translate the question is in how much water is available. And then, of course, I have regulations that impose me to release part of the water for environmental flow, etc. But this is the basic question, water resources availability. And you may think that it's a trivial question, it's not. This is the most challenging problem for an engineer dealing with water resources management. I would say, okay, let me say one of the most challenging. You may think that it's an easy problem to solve. Actually, we often resolve this problem by experimenting, like we project an aqueduct, and the aqueduct takes water from a lake or from the groundwater or from a river, and then we see what happens. So after 10 years, we may realize that the groundwater table has lowered a lot, and then we realize that we cannot take that water because it's not available, and therefore we have to reduce it. So this is still a challenging problem. And as I said, it's classical. So you can find these issues also in classical textbooks, but I will introduce some new considerations based on the concept of sustainability. Okay. First of all, it depends, the method that you follow to assess water resources availability depends on your water source. And therefore, your water source may be, typically is, a lake, a surface water body, or a groundwater body. And if, first of all, let me recall what is a water body. It's a body of water with storing a significant volume of water resources. So it's a water storage that is capable of hosting significant volume of water resources. Let me use the word storage in a very dynamic way and wide sense, because as I mentioned to you, a river is not storing at each time step a significant amount of water. But if you look at, for instance, the annual volume of water that is conveyed by a river, it becomes significant. So the reason why I used the term storage in my definition instead of body is because storage is it's clearer. But actually the definition is a water body is a body of water that is able to provide a significant volume of water for human, volume of fresh water to convey, okay? Either through storage or through flow. Okay, so it depends, the technique that you use to assess water resources availability depends on the body of water that you are, on the water body that you are considering. We can divide water bodies in surface water bodies and groundwater bodies. Typically, we can divide surface water body in reservoirs and rivers. We don't have the same subdivision for groundwater bodies because actually groundwater bodies are